Even before the concept of vaccines existed, the human body already possessed its own form of protection against the invisible threats of the world: natural immunity. This defense is not just a passive barrier, but a highly sophisticated biological system composed of specialized cells, signaling proteins, and an adaptive memory formed through direct contact with pathogens. When the body encounters a virus, it activates an internal protocol designed to contain, eliminate, and most importantly, remember that invader for future encounters. This natural immune response is the foundation upon which all vaccine science would later be built, because vaccinating is, essentially, teaching the body how to defend itself before the first real attack even occurs. Human immunity is divided into two major fronts: innate immunity and adaptive immunity. Innate immunity is the first line of defense, ready to act within minutes of an infection. It is not specific. It reacts the same way to different agents. It includes barriers like the skin, nasal mucus, gastric acid, and cells such as macrophages and neutrophils, which patrol the body for signs of danger. Adaptive immunity, on the other hand, is more refined. It kicks in a few days after exposure to the pathogen, when T and B lymphocytes are activated. These lymphocytes recognize specific structures of invaders, such as viral surface proteins, and create personalized responses. This is where immunological memory is born, a unique ability of the organism to remember past infections and respond faster and more forcefully in future encounters. When a person contracts a viral disease and recovers, their immune system records the signature of that virus. This memory allows the body, upon a second exposure, to produce specific antibodies within hours, preventing the virus from spreading. This explains, for instance, why someone who has had measles once rarely gets sick from it again. In this case, natural immunity is acquired through direct confrontation with the infection. But this process is not always safe. Some diseases leave serious after effects or can be fatal. Vaccines were developed precisely to simulate this learning process without exposing the body to real risk. But to reach this technological step, it was first necessary to understand how the body already knew how to defend itself on its own. Another fascinating aspect of natural immunity is its evolutionary legacy. Over thousands of years, human populations developed progressive resistance to various pathogens. The genetic code of certain groups contains adaptations against regional diseases such as malaria, bubonic plague, or even local flu strains. This inherited resistance, however, is limited and often insufficient in the face of new viruses or mutations, as in the case of HIV or SARS-CoV-2. In such scenarios, the body has no prior memory or ready defenses, and the infection spreads more easily. That is why, even with an active immune system, natural protection has its limits, and science had to step in with artificial solutions based on the principles of this organic defense. Immunity also varies depending on factors like age, nutrition, stress, sleep, and the presence of other diseases. Newborns, for example, have an immature immune system, but receive passive antibodies from their mothers through the placenta and breast milk, a temporary form of natural immunization. Older adults tend to have a less effective immune response, making them more vulnerable to severe infections. These physiological aspects explain why vaccination campaigns prioritize certain groups and why not everyone responds the same way to the same vaccine. Science had to carefully map these nuances to develop vaccines that are safe, effective, and adapted to human diversity. Finally, natural immunity is not infallible. Viruses such as influenza mutate frequently, tricking the immune system and requiring constant updates to vaccines. Dengue viruses, on the other hand, have multiple serotypes. Contracting one does not guarantee protection against the others, and a new infection can be even more severe, a phenomenon known as antibody-dependent enhancement. These challenges have taught scientists that immunity is a complex dance between body and virus, a molecular battlefield in constant motion. And it was within this unstable territory, between natural defense and persistent threat, that the impulse to anticipate infection emerged, by vaccinating the body before the enemy ever arrives. Long before Edward Jenner and modern science, ancient civilizations had already sensed something instinctive about immunity. Those who survived certain diseases seemed unlikely to fall ill again. This observation led to the emergence of the first forms of inoculation. Empirical practices aimed at deliberately provoking a mild infection to protect against more severe versions. Historical records indicate that as early as the 6th century after Christ, Chinese physicians and Indian monks were performing rudimentary procedures to confer resistance to smallpox, one of the deadliest diseases in human history. Although they had no understanding of viruses, antibodies, or the immune system, these cultures developed variolation techniques, a direct ancestor of modern vaccination, marking the unofficial beginning of science's battle against epidemics. In China during the Tang dynasty, and later under the Song dynasty, documents describe practices in which smallpox scabs were crushed and applied to the nostrils of healthy children. This method, known as nasal insufflation, involved inhaling an attenuated form of the disease, collected from patients who had survived the infection. The idea was simple, yet bold: induce a mild form of the illness to ensure lifelong immunity. Although many cases were successful, the risk of severe infection and even death was real. Still, in times of endemic mortality, the benefits were often considered greater than the risks. In some regions, this procedure became a kind of mandatory ritual, carried out by itinerant physicians and sanctioned by local authorities. In ancient India, Ayurvedic records mention similar methods, in which pus from smallpox sores was inoculated into small incisions on children's skin. These practices, performed by traditional healers, were also based on the principle of controlled exposure. Knowledge was passed down orally or through medical manuscripts, and the success of each application depended on the practitioner's experience. Though highly empirical, these techniques demonstrated an early understanding of acquired immunity. Long before germs were discovered, they were courageous attempts to master biological chance through repetition and observation. The medieval Islamic world also recorded similar experiences. Persian and Arab physicians such as Rhazes and Avicenna documented infectious diseases and suggested that some individuals, once ill, became protected against future infections. While they did not develop systematic inoculation practices like those in East Asia, these scholars helped preserve and disseminate medical knowledge that would later be rediscovered by Western science. It is important to note that the spread of such ideas was often linked to trade routes, religious pilgrimages, and migration, allowing local knowledge to cross continents and enrich the medical imagination of other cultures. Despite its advances, variolation was imperfect and dangerous. Inoculated individuals could develop severe cases and become sources of contagion, unintentionally contributing to outbreaks. Furthermore, without standardized doses or control over the virulence of the material used, results varied widely. Nevertheless, its relative efficacy, observed empirically, led to widespread adoption, especially in imperial China, where it was eventually endorsed by court officials. The method crossed centuries and oceans, later reaching the Ottoman Empire, and through accounts like that of Lady Mary Wortley Montagu, being introduced to Europe as early as the 18th century. These ancient inoculation practices are a reminder that vaccination did not emerge suddenly, but evolved over centuries. They were the starting point of a deeply human pursuit, the desire to control disease through intelligence, even when scientific knowledge was still in its infancy. By observing patterns, testing techniques, and confronting fear, these societies planted the seeds of one of modern medicine's greatest breakthroughs. And though they lacked microscopes, laboratories, or DNA, their rudimentary methods all paved the way for the most powerful idea in immunology, teaching the body to win before it's even attacked. Among all the diseases that have afflicted humanity, few have been as deadly, feared, and influential as can smallpox. For millennia, it devastated cities, armies, and entire continents with ruthless efficiency. With mortality rates ranging from 20% to 30%, and survivors often left disfigured or blind, smallpox was far more than just an infection. It was a cultural terror, a landmark in the history of public health, and the primary catalyst for the birth of the modern concept of vaccination. It is estimated that, in the 20th century alone, it killed over 300 million people. Its impact was so profound that it shaped geopolitical dynamics, inspired medical theories, and triggered the largest eradication campaign ever conducted by the World Health Organization. Smallpox is caused by a virus from the orthopox virus genus. particularly the variola major strain. It spreads through respiratory droplets or direct contact, incubating silently for about 12 days, before symptoms erupt suddenly: high fever, intense pain, malaise, and then a painful rash that evolves into purulent pustules across the body. These lesions are highly contagious, and the disease progresses rapidly. The immune system is pushed to its limits, and complications such as pneumonia, encephalitis, or septicemia are common. Those who survived often carried deep scars or permanent damage, such as blindness. For centuries, smallpox was seen as an unavoidable curse. Outbreaks would decimate entire populations, especially in densely populated areas or those with high traffic from pilgrims and merchants. The disease followed armies, crossed borders, and with European colonization was carried to the Americas, Africa, and Asia, wiping out indigenous populations that had never been exposed to the virus. In many of these regions, smallpox became an involuntary weapon of imperialism, destroying societies with no prior immunity. Catastrophic epidemics in Mexico, Peru, and North America contributed to the collapse of entire civilizations. The history of smallpox is also the history of immunological inequality among peoples. Faced with this recurring terror, humanity desperately sought preventive measures. Variolation, already practiced in Asia, began to gain ground in Europe in the early 18th century, with positive reports coming from the Ottoman Empire and China. The procedure involved introducing secretions from the sores of mildly infected patients into healthy individuals. Though effective in most cases, it still carried risks, and public fear was understandable. It was in this context that an English physician, Edward Jenner, made a revolutionary observation. Milkmaids who had contracted the bovine version of smallpox, cowpox, seemed immune to human smallpox. This idea would change the world. In 1796, Jenner conducted his historic experiment. He extracted pus from a cowpox lesion on a young milkmaid named Sarah Nelmes and inoculated it into an 8-year-old boy, James Phipps. The boy became mildly ill, but recovered quickly. Weeks later, Jenner exposed him to human smallpox, and he did not get sick. The boy was immune. For the first time, a controlled and safe infection had produced specific protection against a deadly disease. Jenner called this method vaccination, in honor of the word vacca, Latin for cow. Thus was born the modern principle of immunization. Jenner's discovery was met with enthusiasm by some and skepticism by many. Conservative doctors, religious groups, and parts of the general population resisted the idea of injecting animal material into the human body. However, the results spoke for themselves. Within a few decades, vaccination campaigns spread across Europe and the Americas, drastically reducing smallpox outbreaks. Over the 19th century, governments began adopting public vaccination programs, often mandatory. The idea that a deadly disease could be prevented without direct suffering began to seem not only possible, but necessary. And it all began with an observation, a bold hypothesis, and the courage of a doctor to challenge the status quo. Smallpox, therefore, was much more than the first disease to be fought with vaccines. It was the natural laboratory where a scientific revolution was born. It was the first disease to be targeted by a global eradication campaign, and to this day, the only one completely eradicated from Earth, declared extinct by the WHO in 1980. Its story is a powerful reminder of the impact scientific knowledge can have on human reality, and it is also proof that, even in the face of fear, doubt, and death, science can learn, adapt, and ultimately prevail. By the end of the 18th century, the world still lived under the constant terror of smallpox, a disease that disfigured faces, blinded children, and buried entire families. Medicine at the time tried to contain this scourge with methods like variolation, a primitive and risky way to induce immunity. But it was the English physician Edward Jenner in 1796 who took the decisive step that would forever change the history of immunity and public health. Observing that women who milked cows rarely seemed to contract smallpox, Jenner had one of the most important insights in science. Perhaps prior exposure to a milder form of the virus could protect against the deadly disease. What he tested, documented, and proved with courage would become the foundation of all modern immunology: vaccination. Jenner's reasoning was bold. He knew that many milkmaids contracted a mild illness called cowpox, characterized by lesions on the hands, but rarely progressing severely. Based on local accounts, he realized these women seldom got smallpox, even during outbreaks. Determined to test this hypothesis, Jenner collected pus from a cowpox lesion on the hand of a milkmaid named Sarah Nelmes and inoculated it into an 8-year-old boy, James Phipps. Days later, the boy developed a mild fever and some discomfort, but quickly recovered. Weeks afterward, Jenner exposed him to infectious material from human smallpox. The result was astonishing. James did not develop the disease. He was immune. The discovery was not met with immediate celebration. Many physicians at the time considered the experiment unethical, unsafe, or even absurd. After all, Jenner had deliberately introduced infectious material into a child, an unthinkable act by today's standards. But he was methodical. In 1798, he published his findings in An Inquiry into the Causes and Effects of the Variolae Vaccinae, presenting evidence from additional cases, including vaccinated adults who were later exposed to smallpox without falling ill. The term vaccine emerged there, derived from the Latin word vacca, cow, in homage to the bovine origin of the material. The idea of using a controlled infection to teach the body to defend itself before danger arrived was now officially launched. Over time, the results spoke for themselves. Jenner's method was safer than traditional variolation and offered long-lasting immunity with minimal side effects. Within a few years, physicians across Europe and North America began replicating the technique. Vaccination campaigns were soon organized by governments and religious institutions, and for the first time in history, humanity glimpsed the real possibility of controlling a disease before it struck. Jenner became a public figure, welcomed by kings, scientists, and medical societies. But beyond fame, the true impact of his discovery was practical. Smallpox mortality rates dropped dramatically in vaccinated regions. Despite the success, resistance did not disappear. Many sectors of society viewed the vaccine with suspicion. Religious leaders claimed it was blasphemous to insert animal-derived material into the human body. Others feared that the side effects could be worse than the disease itself. Satirical cartoons of the time depicted vaccinated individuals growing horns or developing bovine traits, fueling public fear. However, as smallpox receded, public perception began to shift. The effectiveness was undeniable, and Jenner's vaccine became a symbol of a new paradigm: scientific prevention. Jenner's revolution transcends his era because it introduced three fundamental concepts: that the body can be biologically trained to defend itself, that this can be done safely and strategically, and that the widespread dissemination of evidence-based medical practices can transform public health on a global scale. His work paved the way for scientists in the decades that followed, such as Pasteur, Koch, and Sabin, to develop vaccines for rabies, typhoid, tuberculosis, and polio, all based on the same logic of simulating the enemy to prepare the defenses. Jenner died in 1823, but his legacy continued to grow for 2 centuries. His name is engraved on monuments, coins, and books, but his true legacy lives on in every dose administered, every child protected, every outbreak prevented. The vaccine, born from cow pustules and the courage of a rural doctor, inaugurated the age of preventive medicine and offered humanity for the first time the chance to anticipate death and overcome it. With the seed planted by Edward Jenner, the medical world began to understand that it was possible to induce immunity without requiring a person to face the most dangerous form of a disease. But it was through the work of Louis Pasteur, and already in the 19th century, that vaccination ceased to be an empirical experiment and became a science grounded in microbiology, systematic experimentation, and a deep understanding of infectious agents. Pasteur not only expanded the concept of vaccines, he demonstrated that specific microorganisms caused specific diseases, and that they could be domesticated, weakened, and used to save lives. Thus was born scientific vaccination, precise, laboratory-based, and replicable. Louis Pasteur was trained as a chemist, but it was his interest in fermentation and spoilage that led him into microbiology. While studying wine and milk, he discovered that invisible microorganisms were responsible for deterioration. This led him to propose the germ theory of disease, at a time when many physicians still believed in mystical causes or imbalances of bodily humors. Pasteur showed through rigorous experiments that specific microbes caused specific diseases, and that it was possible to weaken these agents in the lab. This idea was revolutionary. If germs could be controlled, then perhaps it was also possible to teach the body to defend itself without becoming ill. The decisive moment came with Pasteur's experiments on rabies. Rabies was a fatal disease that caused extreme suffering, progressive paralysis, and inevitable death after symptoms appeared. There was no cure. Pasteur, together with his collaborator Emile Roux, began studying the rabies virus in the brains of infected animals. After successive passages through rabbits and controlled drying of neural tissue, they obtained an attenuated version of the virus. In 1885, a 9-year-old boy named Joseph Meister was attacked by a rabid dog and brought to Pasteur. Though not a physician, Pasteur administered a series of injections with the weakened virus. The boy survived. For the first time, a vaccine had been rationally developed in a laboratory against a deadly viral disease. The impact was immediate. The experience with Joseph Meister made Pasteur an international public figure. Scientists and governments began investing in the creation of research institutes modeled on his work. In 1888, the Our Pasteur Institute was founded in Paris, dedicated to vaccine production, microbiological research, and the training of scientists. Vaccination moved from being an isolated practice to a public health policy based on reproducible science, with quality control, laboratory protocols, and epidemiological goals. Vaccines against typhoid, cholera, tuberculosis, and anthrax emerged in the following decades, all inspired by the methods and principles established by Pasteur. Unlike Jenner, who used raw biological material without knowing the exact pathogenic agents, Pasteur knew the microorganisms involved, understood how to manipulate them, and sought ways to weaken them without eliminating their ability to stimulate the immune system. This technique, known as attenuation, became standard in many vaccines developed later. Pasteur also argued that immunization should be administered before exposure to the pathogen as a preventive measure, but his success with rabies, a disease with slow progression, showed that in some cases it was possible to vaccinate even after exposure, provided it was done quickly enough. With Pasteur, vaccination gained a robust theoretical foundation. His germ theory not only supported vaccines, but also transformed medical practice. From it emerged the principles of asepsis, sterilization, quarantine, public hygiene, and bacteriological diagnosis. Medicine shifted from a passive and reactive approach to one that acted preventively based on knowledge of disease-causing agents. Furthermore, Pasteur initiated the era of modern laboratories, centers of applied research with direct impact on public health. Science began to move closer to the people in tangible ways, saving lives. The case of rabies became a turning point. For the first time, humanity controlled a viral disease through microbiological knowledge. Vaccination was no longer a practice of empirical repetition. It became a rational intervention based on understood and replicable biological principles. This conceptual leap allowed scientists in the following centuries to develop vaccines for dozens of other diseases, improving methods, expanding reach, and reducing risks. Louis Pasteur not only saved thousands of lives with his vaccines, he established a scientific and medical paradigm that still supports immunization in the 21st century. The history of vaccines is, at once, a story of scientific progress and of deep social resistance. From the earliest experiments with variolation to the mass vaccination campaigns of the 21st century, hesitation toward vaccines has accompanied their development almost like an inevitable shadow. Distrust, fear, rumors, ideologies, religion, and even authoritarian policies have shaped contexts in which large segments of the population actively resisted vaccination, even in the face of devastating epidemics. Understanding these reactions is not only crucial for interpreting the past, but also essential for confronting today's challenges of misinformation and scientific denialism. As early as the 18th century, when Edward Jenner introduced smallpox vaccination using bovine material, criticism arose immediately. Satirical cartoons published in the press suggested that vaccinated individuals might develop cow-like features, with horns or snouts emerging from their bodies. There was widespread discomfort with the idea of introducing animal substances into the human body, something seen as unnatural or even sinful. Various religious leaders accused vaccination of interfering with divine will, claiming that diseases were punishments from God and should not be artificially prevented. Other groups, influenced by libertarian views, regarded vaccines as a violation of bodily autonomy and individual freedom, a theme that would echo through the centuries. With the institutionalization of vaccination, especially during the 19th century, the conflicts intensified. In the United Kingdom, the Vaccination Act of 1853 made smallpox vaccination mandatory for all children, with penalties imposed on parents who refused. The reaction was swift. Thousands of people began to publicly protest the law, organizing rallies, assemblies, and founding anti-vaccination leagues. The largest of these took place in Leicester in 1885, drawing over 80,000 people. Accusations ranged from severe side effects to conspiracy theories about population control. The movement gained such strength that the British government was forced to implement exemption clauses, and the debate over liberty versus public health became global. In the United States, resistance also found fertile ground. In the late 19th and early 20th centuries, as smallpox and diphtheria vaccination campaigns expanded, many states enacted mandatory laws. In response, organized anti-vaccine associations emerged, such as the Anti-Vaccination Society of America, which denounced medical tyranny. One of the most emblematic episodes occurred in 1905 in the Karst-Jacobson versus Massachusetts case, where the U.S. Supreme Court ruled that the state had the right to enforce mandatory vaccination during an epidemic, provided it adhered to scientific and ethical standards. This decision established the legal precedent for compulsory public health interventions worldwide. In Brazil, resistance was equally intense and at one point violent. The so-called vaccine revolt, which erupted in Rio de Janeiro in 1904, marked the height of popular rejection. The city was undergoing forced urban reform, with violent evictions, rising poverty, and a population cornered by yellow fever and smallpox epidemics. The government, led by Rodriguez Alves and with Oswaldo Cruz heading public health, decreed mandatory smallpox vaccination with the right to enter homes by force. The population responded with outrage. Protests erupted, streetcars were vandalized, public buildings attacked, and the army was called in. The violence only ceased after military repression. Vaccination was eventually suspended, but the episode showed that, without dialogue and trust, even the best-intentioned science can fail. Vaccine resistance has always found new forms of expression, adapting to changing technological and political contexts. In the 21st century, with the rise of the internet and social media, a new wave of misinformation emerged, amplified by algorithms and organized groups. Rumors about microchips, infertility, genetic manipulation, and conspiracies spread rapidly. During the COVID-19 pandemic, even amid a global emergency, millions of people rejected safe and effective vaccines, driven by fear, distrust, and in many cases, the political weaponization of scientific doubt. Denialism became a public health issue as serious as the virus itself. Despite all of this, history shows that resistance can be reduced when there is transparency, access to clear information, cultural respect, and community engagement. When science engages in dialogue with the population, instead of merely imposing protocols, adherence increases. Initiatives such as school-based vaccinations, support from religious leaders, and empathetic educational campaigns have proven effective in rebuilding trust. The lesson that echoes across the centuries is clear. Science defeats viruses, but only with society's help can it defeat fear. At the heart of every successful vaccine lies a carefully designed biological principle, presenting the immune system with a safe portrait of the enemy, enough to teach the body how to defend itself without causing the actual disease. This task requires precise engineering of the pathogen, and this is where two foundational pillars of classical vaccination come into play: inactivated vaccines and live-attenuated vaccines. These two approaches have dominated immunology for over a century and continue to protect billions of people worldwide. Understanding how they work is essential to grasp how the human body can anticipate threats before they strike. Live attenuated vaccines are made from living viruses or bacteria that have been weakened in the lab, so they can no longer cause disease in healthy individuals, but still retain their recognizable structure for the immune system. Attenuation can occur through repeated passages in non-human cells, exposure to controlled temperatures, or the selection of less virulent mutations. The result is an organism that is almost identical to the real pathogen, but replicates slowly and is quickly neutralized by the body's defenses. Notable examples include vaccines for measles, mumps, rubella, and yellow fever, Because they closely resemble the original pathogen, these vaccines generally elicit strong and long-lasting immune responses, often with just 1 or 2 doses. Inactivated vaccines, by contrast, use viruses or bacteria that have been killed chemically or by heat, so they cannot replicate or cause any form of active disease. Nonetheless, they retain antigens, surface structures recognized by the immune system. This technique requires careful formulation, as the immune stimulus is weaker than in live vaccines. For this reason, inactivated vaccines typically require booster doses and adjuvants, which enhance the immune response. Classic examples include vaccines for hepatitis A, injectable polio, cholera, and rabies. The main advantage of inactivated vaccines is safety. They can be administered even to individuals with compromised immunity, such as transplant recipients and cancer patients. The choice between attenuated and inactivated vaccines depends on several factors: disease severity, pathogen stability, distribution logistics, characteristics of the target population, and specific risks. Attenuated vaccines, for instance, require a strict cold chain, as live microorganisms are temperature sensitive. Inactivated vaccines are more stable and can be stored for longer periods, facilitating distribution in regions with limited infrastructure. However, they require multiple doses, which demands an efficient healthcare system to ensure full coverage. Both methods, despite their age, remain successful because they embody the fundamental principle of immunization: to expose without harming, to teach without hurting. Another important aspect is how these vaccines are recognized by the immune system. Because they replicate within the body, attenuated vaccines stimulate both humoral antibody and cellular T-cell responses, offering broader immunity. Inactivated vaccines, which do not multiply, rely more heavily on adjuvants and generally induce predominantly humoral responses. Modern science has refined these techniques, creating combined, multivalent, and even nanotechnology encapsulated versions to enhance efficacy and reduce side effects. Many current childhood vaccines, for instance, combine multiple antigens in a single dose, protecting against several diseases at once. The logistical and scientific challenges in producing these vaccines are immense. It requires cultivating large quantities of pathogens, isolating and purifying them, then inactivating them without damaging their critical antigens. After that, they must be rigorously tested in animal and human models to ensure safety, efficacy, and stability. This process can take years. Still, the results justify the effort. Vaccines like those for polio and yellow fever have saved millions of lives and nearly eradicated once global epidemics. What the public perceives as just a quick jab in the arm is, for science, the culmination of complex biological engineering, biosafety protocols, and strict quality control. These two models, attenuated and inactivated, have formed the backbone of immunology for over 100 years. Today, even with the emergence of advanced technologies like messenger RNA, classical vaccines remain essential, especially in low-income countries where the infrastructure for genetic vaccines is still limited. The longevity of these techniques proves that even as science evolves, certain principles remain valid and effective, particularly those grounded in centuries of observation, refinement, and verification. Ultimately, to vaccinate is to use the enemy against itself, and to turn what once killed millions into the key to protecting billions. The global spread of vaccines was never a neutral, linear, or equal process. On the contrary, it unfolded within the context of colonial empires, geopolitical disputes, and deep health disparities between the global north and south. As vaccines began proving effective in controlling diseases like smallpox and typhoid, they came to be seen not only as tools for saving lives, but also as instruments of power, civilization, and social control. This meant that while vaccines did save countless lives, they were also used as tools of political domination, cultural imposition, and often structural exclusion. To understand the global expansion of vaccination is therefore to also understand the contradictions of scientific modernity and the ethical dilemmas of public health. In the 19th century, with the rise of European colonialism, vaccines were introduced across African, Asian, and American colonies as part of so-called hygienic and civilizing missions targeting native populations. Imperial powers were not primarily concerned with protecting the colonized from disease. They aimed to safeguard colonizers and preserve the local labor force essential to resource extraction. Mandatory vaccination campaigns were often imposed without consent, in languages people did not understand, and under threat of punishment. In many cases, vaccines were tested on a large scale without ethical protocols, using indigenous people, enslaved individuals, and marginalized populations as unwilling test subjects. One of the most symbolic episodes of vaccine expansion was the Balmis expedition, organized by the Spanish crown in the early 19th century. In 1803, physician Francisco Xavier Balmis led a naval mission to Spanish colonies in the Americas and Asia to deliver the smallpox vaccine. However, since the vaccine virus could not be stored in refrigerated vials as it is today, Balmis used orphan children as living carriers of the virus, infecting them sequentially to keep the agent active during the voyage. While the mission saved thousands of lives and was a logistical achievement, it also exposed the ethical limits of the time, as it instrumentalized vulnerable bodies in the name of collective good. Despite medical intentions, local populations were deeply distrustful. Many indigenous African and Asian communities viewed vaccination campaigns as extensions of colonial violence, and not without reason. In some cases, vaccines were accompanied by land dispossession, the destruction of traditional knowledge, and cultural repression. Western medicine often dismissed local healing systems, ridiculed ancestral practices, and treated native peoples as subjects in need of correction. Meanwhile, vaccine distribution was deeply unequal. European metropolises received purified, tested doses, while colonies were given leftovers, outdated versions, or sporadic and disorganized campaigns. A symbol of progress, the vaccine also came to represent exclusion. In the 20th century, with the creation of the World Health Organization and the rise of health diplomacy, a more universal vision of vaccination began to take shape. Global eradication campaigns, such as that against smallpox, involved dozens of countries and millions of volunteers, reaching even the most remote regions. Still, logistical disparities persisted. Most vaccines were produced in wealthy nations, with limited stock shipped to developing countries only after domestic demand was met. During health emergencies like the 2009 swine flu and the COVID-19 pandemic, the phenomenon of vaccine nationalism repeated itself. Rich countries stockpiled doses in excess, while poorer nations waited months or years to begin immunizing their populations. The geopolitics of vaccination made one thing clear: science alone does not ensure health justice. Even when vaccines exist, access depends on infrastructure, diplomacy, political stability, and global cooperation. Programs like Gavi, the Global Alliance for Vaccines, and COVAX have sought to address this imbalance, but continue to face economic barriers, local resistance, and ideological sabotage. Moreover, the colonial past still shapes vaccine perceptions. In many African and Asian countries, fears of secret experiments and contaminated vaccines persist, fueled by unresolved historical abuses. Even so, the benefits of vaccines have spread. Today, despite all the challenges, vaccination campaigns reach billions of people each year, preventing millions of deaths from measles, polio, tetanus, whooping cough, and hepatitis. Developing countries, with support from international organizations, are building their own production and distribution networks. Yet the lesson remains: immune protection is only real when it is collective, and only just when it is universal. By definition, a vaccine does not protect just the individual. It is a pact of trust between science, society, and ethics, and it only functions fully when everyone has access, understanding, and the freedom to choose. Mass vaccination represents one of the greatest achievements of modern public health, not only because it protects individuals, but because it creates collective protective barriers that can stop a virus or bacterium from circulating within an entire population. This principle makes disease eradication possible, not merely controlling outbreaks, but eliminating the pathogen entirely from the planet. Science has shown that this is achievable, but the process requires something even more difficult than developing effective vaccines. Convincing millions of people across diverse cultural, economic, and political contexts to get vaccinated within a coordinated and strategic time frame. The logic behind mass vaccination is based on the concept of herd immunity. When a critical percentage of a population is immunized against a transmissible disease, the chain of infection is broken. This means that even those who are not vaccinated, such as newborns, immunocompromised individuals, or people who do not respond to the vaccine, are protected because the virus cannot find enough hosts to spread. The required coverage varies by disease. In the case of measles, which is highly contagious, coverage must exceed 95%. For polio, 80% may suffice. Success, therefore, depends not just on vaccine efficacy, but on large-scale public adherence. A historic example of complete success was the utter eradication of smallpox, officially declared by the World Health Organization in 1980. After centuries of epidemics, millions of deaths and national campaigns, the final effort was global beginning in 1967. Strategies like ring vaccination, immunizing the close contacts of each case, the use of bifurcated needles to speed application, real-time outbreak mapping, and community engagement helped eliminate smallpox, first in urban centers, then in remote rural areas. The last natural case was recorded in Somalia in 1977. No other human infectious disease has been eradicated since, but this achievement proved that, with organization, knowledge, and political will, even humanity's oldest enemies can be defeated. Other mass vaccination campaigns have also produced remarkable results. Polio, for instance, has been eliminated from nearly all continents thanks to decades of widespread oral vaccination. Countries like Brazil carried out massive campaigns with the iconic Zegotinha character, mobilizing schools, churches, radio stations, and medical teams to immunize children door to door. The strategy went beyond vaccine delivery. It involved public education, combating misinformation, and a national logistics system based on mobile clinics, refrigeration, and population databases. Today, polio persists only in a few countries with geopolitical instability, such as Afghanistan and Pakistan, where social distrust and armed conflict obstruct universal access. Mass vaccination has also played a key role in drastically reducing diseases like measles, rubella, diphtheria, and whooping cough. The introduction of unified vaccination schedules, combined with school-based campaigns and booster drives, has allowed millions of children to grow up without facing epidemics that were common just decades ago. In some countries, such as those in Scandinavia, Japan, and Cuba, vaccination coverage consistently exceeds 95%, making these diseases nearly non-existent. However, in countries with fragile health infrastructure or strong anti-vaccine movements, sporadic outbreaks still occur, demonstrating that eradication requires continuous effort and permanent epidemiological surveillance. The COVID-19 pandemic offered a new global laboratory for mass vaccination. For the first time in history, billions of doses were distributed in under 2 years. In an unprecedented international operation, health systems had to adapt to high demand, temporary vaccine shortages, the transportation of temperature-sensitive immunizers, and pressure for speed and transparency. Despite the challenges, mass vaccination managed to reduce deaths, hospitalizations, and dangerous virus mutations, even amid the inequality between rich and poor nations. However, it also exposed weaknesses in the global system. Fake news, vaccine hesitancy, political populism, and uneven distribution revealed that science alone is not enough. It requires dialogue, public trust, and social justice. Technically, mass vaccination requires meticulous planning, from large-scale production of immunizers to storage, cold chain transport, staff training, digital registration systems, mass communication campaigns, and active outreach strategies. Every step is critical. Logistical or communication failures can compromise the entire operation, For this reason, many countries have created national immunobiological institutes, such as the Butantan Institute in Brazil or the Serum Institute in India, to ensure health sovereignty and agility in campaigns. In such cases, vaccination becomes more than a medical decision. It becomes a public policy of the state. Ultimately, disease eradication is a rare but achievable milestone. It involves decades of research, intergovernmental commitment, international funding, and most importantly, public trust. This trust, often built through effort and empathy, is what transforms vaccines into collective shields. Every time a disease disappears from a country or continent, it's because thousands of professionals, scientists, communicators, and citizens decided together to act before collapse. And this logic of anticipation is what makes mass vaccination not only a health strategy, but a model of civilization. For centuries, vaccines relied on weakened viruses, inactivated bacteria, or fragments of microorganisms cultivated and manipulated in laboratories. This model, while effective, required long production times, complex infrastructure, and living biological materials. But in 2020, at the peak of the COVID-19 pandemic, a previously promising technology emerged as the protagonist of the largest vaccination campaign in history: messenger RNA vaccines. They not only represented a breakthrough in emergency response speed, but also inaugurated a new era in immunological science, faster, more precise, and with almost unlimited potential. The principle of messenger RNA, mRNA vaccines, is elegant and radical. Instead of introducing the virus or a part of it into the body, as in traditional vaccines, the human body is temporarily instructed to produce a viral protein, which the immune system learns to recognize and attack. To achieve this, scientists synthesize in the lab an RNA molecule that codes, for instance, the spike protein of SARS-CoV-2, the structure that allows the virus to enter human cells. This RNA is encapsulated in lipid nanoparticles and injected into the patient's arm. Once inside the cells, the RNA acts like an instruction manual. The cell produces the target protein, which is then presented to the immune system, without ever causing an actual viral infection. This technology has multiple advantages. The first is development speed. Once the genetic code of the novel coronavirus was sequenced in January 2020, labs like BioNTech and Moderna could immediately begin synthesizing the corresponding mRNA. In less than a year, mRNA vaccines were tested, approved, and mass distributed, something unimaginable with conventional techniques, which would have required virus cultivation, purification, and slower testing. Furthermore, the mRNA platform is highly adaptable. It can be quickly modified for new variants or emerging diseases simply by changing the RNA sequence. This opens the door to personalized vaccines against cancer, HIV, seasonal flu, and even autoimmune diseases. Another major advantage of mRNA vaccines is the absence of infectious material. Since they do not use actual parts of the virus, only its synthetic genetic instructions, the risk of severe side effects from viral replication is practically zero. In addition, RNA does not enter the cell nucleus or alter human DNA. It is rapidly degraded after completing its function. The immune response it generates is strong, producing neutralizing antibodies and activating T cells. This explains why mRNA vaccines against COVID-19 achieved high efficacy rates, even against aggressive variants like Delta and Omicron. However, the new technology also brought challenges. Messenger RNA is an extremely unstable molecule, degrading easily when exposed to heat, light, or enzymes. As a result, the first vaccines required ultra-cold storage, around 70 degrees Celsius, which made distribution difficult in poorer countries or remote areas. Over time, more stable formulations were developed and supply chains adapted, but the episode highlighted the need for technological infrastructure and equitable access to innovation. Additionally, the novelty of the technology sparked public skepticism, fueling conspiracy theories about genetic modification, surveillance, and long-term effects, though none of these claims had any scientific basis. The success of mRNA vaccines against COVID-19 opened a new chapter for immunology. Companies and universities are now investing in applications for specific cancers like melanoma and lung cancer, where the vaccine teaches the immune system to recognize mutant proteins on tumor cells. Other research focuses on vaccines against HIV, malaria, hepatitis C, and even rare diseases, all using the same principle, delivering a safe, temporary genetic message to train the body. This represents a paradigm shift. The vaccine is no longer a fixed biological product, but an immunological programming platform, adaptable, scalable, and potentially universal. This revolution was only possible thanks to decades of quiet research. Scientists like Katalin Karikó and Drew Weissman, initially overlooked, spent years refining techniques to stabilize RNA and reduce its inflammatory effects. Their discoveries, published long before the pandemic, were critical to the rapid COVID-19 response. The Nobel Prize in Medicine awarded to them in 2023 recognized not only the impact of their work, but also the value of basic science, persistent and patient, even when its results appear only in times of crisis. With messenger RNA vaccines, humanity has taken a technological leap comparable to the discovery of antibiotics or the decoding of the human genome. It marks the birth of a new generation of immunizations, potentially safer, faster, and more customizable. But like any scientific revolution, it also demands responsibility, equity in access, ethics in application, and transparent dialogue with the public. Because in the end, a vaccine is more than molecules or technology. It is a pact of trust between science and society. Despite the remarkable advances in immunological science and the rapid response to the COVID-19 pandemic, today's vaccination challenges go far beyond biotechnology. The world now faces a paradoxical situation. Even with effective and accessible vaccines, millions of people remain unprotected due to misinformation, active rejection, or structural inequalities. The current reality is shaped by the simultaneous presence of highly mutable new viral variants, globalized denialist movements, and a silent yet dangerous social phenomenon, pandemic fatigue. Together, these factors form the new battleground between science and viruses. The emergence of SARS-CoV-2 variants, such as Delta, Omicron, and their subvariants, revealed the extraordinary adaptability of RNA viruses. By mutating the spike protein, the main target of mRNA vaccines, these variants manage to partially bypass acquired immunity. Although vaccines remain effective at preventing severe illness and death, their ability to block infection has waned over time, requiring booster doses, updated antigens, and combined prevention strategies. This undermines the public perception that vaccines should work once and for all, and highlights the need for ongoing communication with the population about the evolutionary nature of viruses. Alongside this biological challenge lies an even harder one: scientific denialism. Fueled by social media, populist influencers, algorithmic misinformation, and conspiracy theories, the anti-vaccine movement has taken on a new shape in the 21st century. It no longer centers solely on side effect concerns. Instead, it intertwines with political, religious, and identity-based narratives, emotionally opposing scientific authority, globalism, and institutionalized medicine. In several countries, this has led to active vaccine refusal, sabotage of public campaigns, and even attacks on health professionals. For some, science is seen as a symbol of freedom and life. For others, it has become a perceived tool of control and manipulation. In Brazil and many other nations, immunization campaigns that once achieved over 95% coverage have started to decline, particularly among children. Previously controlled diseases like measles and polio have re-emerged. Part of this is due to pandemic fatigue, the emotional and psychological exhaustion following years of health emergencies, quarantines, family loss, and information overload. Many well-informed people began avoiding news, neglecting vaccine schedules, and rejecting new doses simply out of burnout. This has created immunological gaps through which contagious diseases have resurfaced, even while vaccines remain available and effective. Another key factor is the impact of fake news, which spreads faster than the vaccination campaigns themselves. Myths about vaccines causing infertility, altering DNA containing microchips, or causing sudden death are false, but they reach millions of phones in seconds, often appearing credible. Studies show that false information is up to 6 times more likely to be shared than truth, because it appeals to fear, outrage, and urgency. Countering this requires more than technical data. It demands rebuilding trust with the public, communicating with empathy, and making science understandable, accessible, and emotionally credible. In response, science has begun to evolve in how it communicates. Health institutions now invest in campaigns with simple language, social media presence, short videos, podcasts, and trustworthy digital influencers. Scientists are leaving their labs to engage in public discourse, giving interviews, writing opinion pieces, and directly interacting with society. Scientific education programs in schools, journalist training courses, and media literacy have become key strategies. Because in today's world, it is not enough to have a working vaccine, we need a working narrative around it. Meanwhile, governments and international organizations are rethinking how to make vaccination campaigns more resilient and inclusive. This involves diversifying vaccine technologies, investing in local production, aligning vaccine schedules with school systems, enabling off-hours vaccination, and training community health workers to promote care with empathy. The goal is to anticipate future outbreaks with robust, flexible plans, not merely react when the system collapses. Today's challenges demonstrate that vaccination in the 21st century is not just a medical act. It is a social, political, and communicational act. Viruses mutate, technologies advance, but the key remains unchanged: trust. Without it, no vaccine works. With it, even the most novel and complex ones can become collective shields. Vaccination is as urgent now as ever, but today, more than ever, it is also a continuous effort to rebuild the bridge between science and society. The history of vaccines has so far been a narrative of progressive discoveries and technical adaptations, but what lies ahead is more than a continuation. It is a paradigm shift. The future of immunization is moving toward an era where we won't just react to diseases, but will anticipate and personalize the body's defenses using genetic precision, artificial intelligence, and molecular engineering. Vaccines will no longer serve merely as a collective shield against known viruses. They will become tools of individualized immune programming, capable of preventing, modulating, and even reversing complex biological processes. Welcome to the age of future vaccines. Among the most promising innovations are the so-called DNA vaccines. Unlike messenger RNA, mRNA vaccines, which temporarily instruct cells to produce antigens, DNA vaccines use plasmids, small circular fragments of synthetic DNA that enter cells and directly instruct them to produce the target protein. These plasmids do not integrate into the human genome and are rapidly degraded after antigen expression. Their main advantage lies in thermal stability. DNA vaccines can be stored at room temperature for months, facilitating distribution in low-income countries. Additionally, their production is inexpensive, fast, and highly adaptable. Clinical trials are currently underway for diseases such as Zika, chikungunya, hepatitis B, and even certain types of cancer. Another frontier is the quest for universal vaccines, especially against highly mutable viruses such as influenza and HIV. Instead of focusing on the virus's variable parts, like surface proteins, scientists are now attempting to identify highly conserved epitopes, internal regions of the virus that rarely mutate. By training the immune system to target these fixed areas, it could be possible to develop a single vaccine capable of protecting against multiple variants and subtypes. This same principle is applied in research for a pan-coronavirus vaccine. The goal is clear: to eliminate the never-ending race of seasonal updates and create durable, broad-spectrum immunizations that resist mutation. Perhaps the most ambitious frontier in immunization is therapeutic vaccination. That is, vaccines not for disease prevention but for treatment. In the case of cancer, for example, the idea is to identify specific neoantigens from tumor cells and teach the immune system to recognize and destroy them selectively. Unlike chemotherapy, which attacks both healthy and diseased cells, the cancer vaccine would be highly precise, reducing side effects and increasing effectiveness. Clinical trials with melanoma, breast cancer, and lung cancer patients have already shown promising results. Immunotherapy, previously limited to monoclonal antibodies, now gains tailored vaccine allies based on each tumor's genetic sequencing. Genetic engineering also allows us to envision vaccines that not only protect, but correct immune system errors. In autoimmune diseases such as lupus or multiple sclerosis, researchers are working on tolerogenic vaccines, immunizations that teach the body not to attack itself, restoring immune balance without completely suppressing defenses. For allergic diseases like asthma and rhinitis, vaccines in development aim to modulate the inflammatory response, reducing symptoms long-term. This approach demands a very high degree of personalization, with machine learning algorithms capable of predicting immune patterns and suggesting unique vaccine compositions. Delivery technologies are also evolving. New formats under testing include skin patches with microneedles, which eliminate the need for syringes and allow self-administration, inhalable vaccines for respiratory illnesses, and oral immunizations encapsulated in nanoparticles that resist stomach acid. These innovations not only expand access, but also improve acceptance among needle-phobic individuals, young children, and vulnerable populations. They also enable mass immunization during emergencies with simplified logistics and reduced dependence on trained personnel. The future also lies in data integration. With the advancement of digital health, it will become possible to develop genomic immune passports, where each individual has a personalized map of immune responses, allergies, vaccination history, and genetic susceptibilities. This will enable custom-made vaccines, adaptive boosters, and lifelong personalized immunization plans. Instead of universal vaccine calendars, each person will have a precision immune schedule based on their genetics, lifestyle, geographic location, and environmental exposures. Finally, there is the ethical and social frontier. Every technological revolution brings dilemmas of access, consent, equity, and privacy. Who will have access to personalized vaccines? Who will fund research into neglected diseases? How can we ensure genetic data isn't misused for discrimination? The future of vaccination will only be bright if it is ethical, inclusive, and sustainable. Science moves fast, but it must be matched by public policy, updated legislation, and societal engagement. Vaccinating the body is only part of the challenge. Vaccinating society against fear, inequality, and exclusion is just as vital. Behind every vaccination statistic lies an uncomfortable truth. Access to vaccines has never truly been equal. While some populations receive state-of-the-art immunizations quickly, others wait months or never receive them at all. The history of immunization, from its earliest forms to the era of mRNA vaccines, is intertwined with economic, geopolitical, and racial inequalities. Even when science succeeds in developing effective vaccines, the lingering question remains: who gets vaccinated first and why? The answer almost always involves more than medical criteria. It involves power, money, and political priorities. During the COVID-19 pandemic, the phenomenon of vaccine nationalism exposed this reality. Wealthy countries, with direct access to pharmaceutical companies and the financial resources to secure billion-dollar contracts, acquired billions of doses even before clinical trials were complete. The United States, for example, purchased enough vaccines to immunize its population more than 3 times over. Meanwhile, dozens of countries across Africa, Asia, and Latin America faced months of shortages, relying on donations, multilateral consortia, or diplomatic agreements. The international cooperation system failed to ensure equitable distribution. COVAX, the consortium created to promote vaccine fairness, struggled with dose shortages, logistical hurdles, and a lack of political support. But inequality doesn't just exist between nations. Within each country, there are groups that historically receive vaccines first, and others that are consistently left behind. In wealthy urban areas, access is fast, with well-equipped clinics, clear communication, and consistent availability. In contrast, rural communities, urban slums, indigenous villages, and conflict zones often lack syringes, electricity for cold storage, and trained professionals. Public health messaging often fails to reach culturally diverse populations, and many communities, especially those historically mistreated or experimented upon, distrust the healthcare system. In these contexts, vaccines are sometimes viewed less as protection and more as an external imposition. Vaccine inequality is also rooted in history and structure. For centuries, healthcare systems were designed to serve those closest to centers of political and economic power. Black, indigenous, refugee, quilombola, and migrant populations have long remained on the margins of public health planning. Even when included in vaccination campaigns, they were often treated with top-down approaches, without consultation or participation. The notion that every vaccine is a universal good ignores the fact that access depends on infrastructure, trust, culture, and full citizenship. Science may develop a vaccine in record time, but if it doesn't reach everyone, its collective potential is limited. Moreover, patents and industrial monopolies exacerbate inequality. Many modern vaccines are developed by a small group of multinational corporations protected by strict intellectual property laws. Countries lacking technological or industrial capacity must rely on expensive imports that often arrive too late. Attempts to suspend patents, as proposed by India and South Africa during the pandemic, met resistance from developed nations concerned about economic impacts or loss of innovation control. In this scenario, the vaccine stops being merely a health tool and becomes a geopolitical asset. In response, initiatives have emerged to democratize access to vaccines. Countries like Brazil, India, and South Africa are investing in public vaccine factories, capable of producing generic or licensed immunizations with health sovereignty. Regional consortia, such as the African Vaccine Manufacturing Initiative, aim to create local production hubs. At the same time, global movements are pushing for compulsory licensing, technology transfer, and patent waivers during health emergencies. The message is clear: if a vaccine saves lives, it cannot be treated as a privilege. It must be a universal right, protected by international agreements and driven by global political will. Inequality also impacts vaccine trust. When people see that they only receive older vaccines, long after wealthier groups, or when they're used as test subjects, the result is distrust, hesitancy, and rejection. Science must be accompanied by symbolic justice and historical recognition. Campaigns must be built with representation, include community leaders, respect traditional knowledge, and incorporate diverse voices into health planning. Vaccination is not just an injection. It is dialogue, listening, and respect. Finally, the fight against vaccine inequality cannot be episodic. It must be structural and ongoing. This involves training healthcare professionals in vulnerable regions, maintaining continuous logistics, adapting campaigns to local realities, and above all, treating vaccines not as products but as rights. No scientific breakthrough will be complete while billions of people still wait for a vial that already exists, but for some reason never reaches them. Because when we talk about vaccines, we are talking about the most precious thing science can offer: the chance to live, and to live with dignity. One of the most intriguing, and at the same time least understood, aspects of vaccination is the duration of immunity it provides. When someone gets vaccinated, they often expect long-lasting protection, perhaps even lifelong. But in practice, the immune response induced by different vaccines can vary greatly, depending on the type of vaccine, the target disease, the person's age, whether boosters are administered, and biological factors that remain poorly understood. So how long does a vaccine's protection actually last? Science continues to search for answers, and each answer raises new questions about the limits of the human body, immune memory, and the very concept of protection. Some vaccines offer lifelong immunity with just one or a few doses. This is the case with the yellow fever vaccine, which, according to recent studies, provides lifetime protection after a single dose. The same applies to the measles vaccine when given with the proper booster during childhood. In such cases, the immune system is so effective at memorizing the pathogen that even decades later, re-exposure triggers a fast, efficient, and proportionate response. This immune memory involves not only antibody production, but also the activation of long-lasting T cells, which remain on alert even without further exposure to the infectious agent. However, other vaccines require regular boosters. The tetanus vaccine, for example, is recommended every 10 years. The flu shot is annual. The COVID-19 vaccine underwent multiple updates and booster doses within months. This happens for two main reasons: the mutable nature of the virus and the gradual decline of immune response over time. In some cases, the pathogen mutates frequently, as is typical of RNA viruses, which lack genetic proofreading mechanisms during replication. This means older vaccines become outdated against newer variants, requiring periodic updates. In other cases, even if the virus doesn't change, antibody levels and memory cell activity naturally diminish with time. This decline is influenced by factors such as the vaccinated person's age, nutritional status, health history, presence of comorbidities, and even genetics. Older adults, for instance, have a naturally slower immune system, a phenomenon known as immunosenescence, which weakens both the initial response and long-term memory. For this reason, flu vaccines are formulated in stronger versions for seniors. Meanwhile, people with immunodeficiencies, or those taking immunosuppressive drugs, may not develop adequate immunity even after multiple doses. The duration of protection, therefore, is not a fixed rule, but a probabilistic curve shaped by personal variables. Another important point is that immunity is not all or nothing. Even when antibody levels fall, the body may retain residual cellular responses that, while not preventing infection, can stop it from progressing into a severe condition. This was demonstrated in many COVID-19 studies. Vaccinated individuals, even when infected by variants like Omicron, had lower risks of hospitalization and death, precisely because their baseline immunity remained active. This reinforces the idea that vaccines are not impenetrable walls, but biological shock absorbers, not eliminating risk, but making it manageable. To measure the duration of immunity, scientists conduct longitudinal studies, tracking volunteers for years after vaccination. They monitor antibody levels, activation of T and B cells, incidence of natural infections, and booster requirements. This type of data allows health authorities to adjust vaccine schedules, predict booster needs, and evaluate the true effectiveness of immunizations. Such monitoring showed, for example, that the hepatitis B vaccine, once administered in 3 doses with a booster, may provide lifelong protection after the full initial course, eliminating the need for additional doses in healthy adults. In this sense, the future of vaccines is heading toward a more personalized and predictive model. Instead of mass administering boosters on a fixed schedule, healthcare systems may soon rely on immune surveillance models powered by artificial intelligence and individual biomarkers to determine when someone actually needs a new dose. This would be especially useful for diseases with low circulation but high risk, such as tetanus or typhoid fever, and in cases of therapeutic vaccination for cancer, where the immune response must be adjusted in real time. Lastly, it's important to remember that the duration of protection also depends on collective behavior. A vaccine works best when those around you are vaccinated too. Even if your individual protection starts to wane, being in an immunized environment reduces the chance of exposure, functioning as an external barrier. That's why boosters aren't just for reactivating your immunity. They help ensure the entire community remains safe. Protection is a cycle, and that cycle only completes when every link in the chain is maintained with responsibility and science. From ancient times, when healers inhaled dried smallpox scabs to try to induce resistance, to the modern laboratories manipulating RNA with atomic precision, the history of vaccines is, in truth, the story of humanity's struggle to control the invisible. It is a story of scientific advancement, yes, but also of courage, mistakes, resistance, and collective agreements. Because vaccination has never been merely a technical act, it is a profoundly human gesture. It represents the acknowledgement that our vulnerability can be transformed into protection when we act together, guided by knowledge. Each dose administered carries centuries of discovery and philosophical debates on ethics, freedom, and the common good. Each vial contains not just antigens, but fragments of the fight against death, fear, and ignorance. Vaccines have allowed humanity to overcome previously insurmountable barriers, eradicating diseases, protecting the most vulnerable, and living longer and better. They have turned childhoods once cut short by infection into full lives. They have turned epidemiological war zones into landscapes of hope. And all of this was only possible because, at some point, entire communities chose to trust. That trust, however, is never eternal. It must be renewed, explained, cultivated. We live in a time when misinformation spreads faster than viruses, when doubt is manufactured through algorithms, and science is constantly under scrutiny. In this context, getting vaccinated and defending vaccination becomes an ethical act of resistance. It affirms that other lives matter, that the pain of another person affects me, that prevention is a gesture of care that spans generations. Because those who get vaccinated don't only protect themselves, they protect the baby who cannot yet receive a dose, the immunosuppressed elderly person, the neighbor undergoing chemotherapy. Vaccination, then, is an act of civilization. And still, much work remains. Forgotten diseases continue to plague impoverished communities. High-cost vaccines remain a privilege for the few. Social distrust, often rooted in real experiences of exclusion, still distances entire populations from health campaigns. Vaccine equity remains an unfulfilled goal, and the future of immunization will be measured not only by the number of vaccines available, but by how many lives can actually access them. Because as long as children remain unprotected, vulnerable adults are exposed, and entire peoples are left outside the global immune system, science still owes a debt to humanity. Even so, there is hope. The COVID-19 pandemic proved that we are capable of producing billions of doses in record time, adapting technologies, revisiting political boundaries, and investing in collective solutions. It also showed that networks of solidarity among healthcare workers, scientists, teachers, and communicators are powerful when well coordinated. The vaccine remains a bridge between biology and ethics, between the lab and the public square, between the individual and the collective. And each successful campaign is more than a goal achieved. It is a silent celebration of what humanity can accomplish when it acts with intelligence and compassion. Ultimately, the story of vaccines is not over. It continues with each new technology, each newly protected child, each disease defeated, and each person persuaded by the strength of science. It is a story still being written, in laboratories, in classrooms, in health clinics, and around kitchen tables. And perhaps when we look back, we'll see in it one of the greatest expressions of our ability to imagine a better world, a world where life is more than survival. It is a conscious choice to care for one another.